so far, so remember, integration means area under the curve. So I know yours is not blue, but yours is at least shaded. So if f is the function, what we're attempting to do with integration is find out what the area is there, right? We just finished using rectangles and trapezoids, right? Rectangular approximation method, trapezoid approximation method. Those work, but they're approximations, okay? So today, we're gonna find, so these two, using geometry, number 2 and 3, using geometry and antiderivatives are the way to find the exact area. So number 1 is an approximation. They're approximations. Better than nothing, but they're approximations. 2, geometry. What do I mean by geometry? Shapes. Shapes we recognize. Squares, triangles, rectangles, shapes like that, right? We've kind of did that with approximation, but now we're going to use them to actually get the exact answer. And then the third way, which we'll do after the quiz, is using antiderivatives. We know how to find antiderivatives, but we've never integrated, we've never found area using antiderivatives. That's what we'll do after the quiz. That's the second part of this unit. Okay? So those are the 3 ways to find area under the curve. Okay? So we're going to tackle number 2 today. Okay? All right, so this looks really, really complicated, but it's really not. It's really not. Okay, so just like everything, so the 3 things we talk about in this class are limits, derivatives, integrals, integration. Everything is related back to a limit, okay? So if we make sure that the subinterval is the same width, so this is kind of what it breaks down to, okay? So let's look at each of this. Okay, so the limit as n approaches infinity. So what I mean by n is the total number. So if I wanted to find area of this part right here using rectangles, how many rectangles would it take for me not to go over? You know how we over and under counted sometimes? How many rectangles would it take for me if I wanted to figure out, if I wanted to do rectangular method, but I didn't want to go over at all, or I didn't want to go under. I wanted to fully calculate how much area was in the blue. How many rectangles would I need? Like 1 rectangle wouldn't work, right? Because it would need like, that could be a rectangle, right? But that's not going to even come close, right? Because there's parts that I'm going to count that don't count, and I'm not even going to count that, right? If I did 2, I could do something like this. That wouldn't work, right? Those are just approximations. Let's see if I did 3. If I did 3, maybe one like that, one like that, right? How many rectangles would it take for me to get just the blue and none of the white?
Probably like 6.
So 6?
2. I think it would be too many to be convenient enough to do.
Yeah, right? Even if you broke it up like, I'm always going to go over, right? Even if I do like that, right? Then I'm not counting some of them, and it's increasing. So how many? It would literally be too many. It'd be an infinite number. The perfect number of rectangles to cover just that blue would be an infinite number, right? An infinite number. That's where this comes from. That's where this comes from. The number of rectangles needed. Number of rectangles needed. It's infinity, right? So if I wanted to do it and only get the blue, it would be an infinite number of rectangles. Okay? That's where that comes from. Where does the E looking guy, that's a Greek symbol. It's sigma. Anytime you see sigma, this guy right here, in math, does anyone know what it means? What you're going to do if you see the Greek letter sigma, what are you going to always do if you see that in math? It's a summation notation, right? It's a summation notation. What does summation mean?
Like the approximate?
No. What is summation? What does the word summation mean? If I want to summate, add it all up, right? Summate means, what does it all mean? You know, like at the end of a trial, it's called a summation because you're bringing it all together. You're adding it all up. You're putting everything together, right? So this is what we call a summation notation. It means a total. You're coming up with a grand total. You're adding it up. Sum means total, right? So you're coming up with a total. A total what? Total area. What are you adding together? Well, what do we add together when we're finding area? What have we been adding up? We've had this long list of things to add up. What have we been adding up?
The area of the rectangles.
That's the summation part. We're adding up. So this is how many rectangles I'm going to need. This is the total area of each rectangle. Add it all up. Okay, this part right here that kind of looks like a curse word. It's not. That represents the function. That represents the function. F of x, g of x, whatever you call it. What is the function? So in terms of the rectangles, right? I know this is going to tell me how many I need. This is going to tell me the total area of each. To figure out area, what do I need from the rectangles? I need two things to figure out area. The width and the length or height, right? The function tells me the height of the rectangles. The function tells me the height of the rectangles. Right? We plugged it into the function and it told me the y value. Y is the height. The last thing is the width. What is that triangle? It's another Greek symbol. What is the triangle? Sometimes you see it in science. Delta. It's delta, right? Anytime you see delta in math, the triangle in math, it means what? A change. It means a change, right? A change in x. Well, what is changing on it? That's the width, right? The x is always the width. So this is the width. So each of these has an important part in what we're doing. One tells me how many rectangles are you going to have. One tells me the area of the rectangles. You're going to add them all up. One tells me the height of the rectangles. One tells me the width of the rectangles. Okay? Now, when we do integrals, we don't have all those parts. We have these parts. It got broken down to these parts. Okay? But all of those are in here. All of those are in here. Okay? You got the function, right? You got the function. Right? This guy means area. You're going to add up area. What do A and B tell us?
Is that the number needed?
There you go. How many are you going to go? Where are you going from? From where to where are you going from? Right? It's the interval. In other words, how many rectangles are you going to need? Which part are we missing? No, we got that. The width, right? There's no width. You got to know how wide the rectangles are, right? That's where this comes from. So why is that dx always been there, and why will it continue to be there? Because we need to know how wide the rectangles are. We got how many rectangles, we got the area, we got the height, but without the dx, we don't know the width of each rectangle. That's why you always see a dx at the end of these problems. Why is there always a dx? Because we need to know the width. They tell us the width, okay? It's important for that, otherwise we don't know how wide the rectangles are. Try finding an area of a rectangle if you don't know how wide it is. You can't do it. You can't do it, okay? So how do we read it? We read it as such. We say the integral of f of x from a to b.
At the beginning, did we do the plus c on this one?
So this one, when we answer it, we'll have a plus c.
Okay.
Yeah, when we answer them. That's a great question. Will there be a plus c? Yes. As long as there's no bounds. No bounds. So if there was no bounds, plus c. If there are bounds, you don't have to do the plus c. That's a great point. Let's put that on here. Okay? Bounds equal no plus c needed. What do I mean by bounds? The a to b. If those aren't there, you need the plus c. If they are there, you don't need the plus c. Okay? No bounds, no plus c needed. Or sorry, if there are bounds, you don't need plus c. Okay? And we'll do them. We'll do them as we go. As we go, I'll explain that. Okay?
Are we using this both notation?
You'll mostly see this one. Occasionally, once in a blue moon, you'll see that guy. You'll see that, and most of you will be like, what? What is that? You have to go back to your notes. But I would say 97 times out of 100, you'll see this guy.
But they mean the same thing.
They mean exactly the same thing, yeah. You just got to know where to look. When you see this guy, you're going to be like, what does all that mean? It means the exact same thing. It's indifferent. One's in limit. It's a limit notation. One's an integral notation. That's the only difference, right? So yeah, so if you see this guy with a limit and a sigma, go back to your notes and see what each part means, okay? But like I said, 97 out of 100 times, you're going to see that guy right there, okay? Because that's more of, this is more of the integral method. All right, so let's take a look. Let's take a look. So let's go to the back. Let's start doing some. Okay, so before we start, we can define the area under a curve from A to B as an integral from A to B. Though, drawing a picture and using geometry. So when I say geometry, I mean shapes, draw a picture. That's what I mean by geometry. Is still a valid method of finding areas. Okay, so for each, what I'm going to do is I'm going to draw a sketch. What am I going to draw a sketch of? The function. The function. So let's look at A. I know the bounds go from 2 to 9, right? But what is the function part? Just the 3, yeah, just the 3. That's the function part, right? This guy right here. That's f of x. That's what I'm going to draw a picture of. I'm going to draw a quick sketch of that from 2 to 9. So from positive 2 to positive 9. How do I draw f of x equals 3? Or how do I draw 3 as a function? Just 3. No 3x, no 3x squared, just 3. Straight line at y equals 3. At y equals 3, yep, just like that. So at 3, it's just going to be, where is it at 2? 3. Where is it at 9? 3. Where is it in between? 3. So that's the function there. My job is to find area under the curve there. So I start at 2, go to 9, I need to find area under the curve. So all this stuff right here. I could make rectangles. I could do antiderivatives. We haven't done that yet, so we're not going to do that one today. But I think the easiest way is, what shape is that? It's a rectangle, right? Find the area of the rectangle. So here you got 7 by 3, 21. Okay, we don't need a plus c because there were bounds. It was from 2 to 9.
Would you not put the units square?
Yeah, you don't have to anymore. Yeah, don't worry about that. When we don't talk about rectangles, yeah, we don't really use it. Okay. All right.
So if every time the function is a constant, do you have to sketch it out, or can you just do, okay.
Yeah. Right, because you know it's going to be, so yeah, I would like if you could do that part in your head, yeah. You know that the function is always going to be 3 height. How wide is it? 7. What's 7 times 3? Makes it easier on yourself. If you need to draw a quick sketch, do it. But you have my permission. You don't need to show that, okay? Back, first time we saw absolute value in this class, I told you, draw a picture. Always draw a picture for absolute value because it's always easier than doing it the other ways, right? So for absolute value, I'm going to draw a picture. This goes from -2 to 1, right? So I'm going to draw a picture real quick from -2 to 1. So -2, -1, 0, 1. So how am I going to draw a picture? I'm just going to plug in numbers. So when I plug in -2, what's y going to be?
-2.
No, +2. When I plug in -1,
1.
right, because this is the function here. Plug in 0, plug in 1, there you go. So the graph from -2 to 1 looks like this. Area under the curve is this, and then this. What shapes are those? Triangles. So you're just finding area of both of those triangles. Okay? So the first triangle is a 2 by 2. What's area of a triangle? How do I find, what's the formula for area of a triangle? There you go. Base times height, length times width, and then just divide it by 2, because it's half of a square or half of a rectangle. So 2 by 2 divided by 2, you get +2. 1 by 1 divided by 2, you get 0.5. So the area would be 2.5. Okay. All right, let's do this guy right here.
Are we ever gonna do, or right now, are we just doing are we integrating off of the x-axis?
Yeah.
Like,
Will we do it off the y? Yes. Later on.
will we ever like go lower? Like,
Below the x-axis? I think on the next page we are.
oh,
Yeah, I think in the next page, I hope in the next page, we're gonna, yeah, because there's a difference there, yeah. For sure, yeah. Okay, so here we go, -3 to +3. I don't know how to do antiderivative for that guy. We haven't learned that yet, so let's draw a picture. From -3 to +3. -3, -2, oops, probably should move a little. 1, 2, and 3. Okay. This is the function. So I'm going to plug in those x values. When I plug in -3, -3 squared is 9. 9 minus 9 is 0. Square root of 0 is 0. First dot goes there. Negative 2. So when I plug in negative 2, I'm going to get 9 minus 4, which is the square root, which is 5. The square root of 5 is not a nice, pretty number. It's between 2 and 3, though. 1, 2. So let's see. Square root of 5 is just above 2. So it's closer to 2 than it is 3. So I'm going to make a dot closer to 2. Negative 1. Negative 1 divided by 1, or sorry, negative 1 squared is 1. 9 minus 1 is 8. The square root of 8 is almost 3. So I'm going to put 1 almost 3. 0. 9 minus 0 is 3. The square root of 3 is, or square root of 9 is 3. So what it's doing is it's creating kind of a, something like that, with a curve. The other side's going to be very similar. If I get 1, 1 squared is 1. 9 minus 1 is 8, so it's going to be very close to 3. 2 is going to give me the same answer as negative 2. And then 3 is going to be 0. Which shape is that? It's actually a half circle. Yeah, it looks like an oval, but the only reason it looks like an oval is because my graph is not to scale. That's it. It's actually a circle. How do I know it's a circle? Because look at the radius. From the center is 3. From the center is 3. If you wanted to check, you could check that too. Because we know this guy here, this guy is 1 square root of 8. So you could do a squared plus b squared equals c squared to do that, and you would figure out it is, in fact, 3. Okay, so it's a half circle. It's a half circle. So we're finding area under the curve. So half circle. So what is the area of a half circle? What is the formula for area of a half circle, I should say? So it's going to be, so area of a full circle is pi times r squared, right? Half circle, divide that by 2. Okay. So we have a circle with a radius of 3. So we have pi times 3 squared divided by 2. So 9 pi over 2. Leave it like that. Okay. So these 3 problems have all been above the x-axis. The ones on the back, we're going to go below the x-axis. So what happens when we go below the x-axis? Here it is right here. So what happens if we're trying to find area under the curve, but we're below the x-axis? You're going to get negative values. So what happens if the area is below the x-axis? Even though area is inherently positive. Like in real life, you can't have a negative area. You can't. But in this case, we do have negative area. Okay? So even though area is inherently positive, a Riemann sum and an integral can have negative values. Okay? Because they're based off this, and this has negative values. Okay? So let's do this one here. So we're going for area. So the function is drawn. We're going for area from negative 8 to 2. Negative 8 to 2. Okay? So the picture is already drawn for you. So negative 8 starts here. Positive 2 ends here. So I'm going to shade the area. So area under the curve is here. Now we have some under the curve. So how do I, or under the x-axis, how do I shade under the curve if it's, you don't, you shade up. So if it's below the x-axis, you shade up to the x-axis. If it's above the x-axis, you shade down to the x-axis. Always shade to the x-axis. Always shade to the x-axis. And I did two different colors because one of them is going to be a negative area and one of them is going to be a positive area. Okay? Okay, so the negative is a triangle. It looks like it's a 4 by 8 triangle, 4 by 8. So area of a triangle is base times height divided by 2. So that's 4 times 8, 32. 32 divided by 2 is 16. So this area is going to be negative 16. Negative 16 because it's below the x-axis. The green is going to be positive. The green is not a shape I recognize. So what I'm going to do is I'm going to break it up into smaller pieces. There's different ways to do this. There's not one way to find area of the green, but you can break it up into smaller pieces. So I would probably do, this is a triangle here. And then what I would probably do is say, hey, if I close this off here, it becomes a square, right? And then I could just subtract the half circle. That might be the easiest. Okay, so the triangle is a 2 by 4. So that's 8 divided by 2, so that's positive 4. So this square that I close off, it actually is a square. It's a 4 by 4 square. So the total here is 16 because it's a 4 by 4, right? But I don't want that part here. So I have to subtract it. So it's going to be 16 minus that triangle. Or sorry, that circle. Well, the circle, it's a half circle, right? Area of a half circle, pi times r squared, divided by 2. So this one has an r of 2. So it would be,
Pi?
yeah, so it would be 2 squared pi over 2.
2 pi?
So it would be, yeah, so it would end up just being 2 pi. That goes there. Okay. I can't subtract 16 minus 2 pi. They're not like terms. So just leave it 16 minus 2 pi. So the area in here is 16 minus 2 pi. So now I'm going to add up all of the areas. So I get negative 16 plus 4 plus 16 minus 2 pi. The 16s cancel out, so you're left with 4 minus 2 pi. So the hardest part about that is that's not even calculus, that's just geometry. That's just figuring out what the areas are. That's the hardest part about it. Okay. All right. So the big thing there is if it's above the x-axis, positive area. Below the x-axis, negative area. And always shade towards the x-axis. So if you're below the x-axis, shade up. If you're above the x-axis, shade down. Okay? All right, so let's do this guy, number 3. So here's the function. They give us the function 3 minus x. So we need to sketch that graph, and then we need to figure out the area from 4 to 8. From 4 to 8. Okay? So I don't care before 4 or after 8. I just want to know what the graph looks like. What does the graph look like? What does f of x look like from 4 to 8? Well, what is that going to look like? When I graph it, what is it going to look like? It's going to be a line, right? It's going to be a line. Yeah, how do we know it's going to be a line? Because x is to the first power. X is to the first power. There's no x squareds or x cubes. It's x to the first power. That means it's going to be a straight line. Okay? So it's going to be a straight line. The 3 means that's the y-intercept, right? Y equals mx plus b. The 3 means that's where it crosses the x-axis or y-axis. What's the slope then? -1. So down 1 over 1, down 1 over 1, down 1 over 1. And that's what it's going to look like. It's going to continue forever, but I don't really care about, all I care about is from 4 to 8. So all I care about is from here to there. That's all I care about. It's under the x-axis, so my answer is definitely going to be negative. It's a trapezoid. It is a trapezoid. If you didn't realize that, you can break it up into a triangle and a rectangle. Like if you didn't see it, you can break it up like this and then find area of the rectangle plus the area of the triangle. Okay, it is a trapezoid. So this is, let's see. This is 5, this is 1, this is 4. So area of a trapezoid's 1/2, base 1 plus base 2 times the height. Base 1, 1, base 2, 5. Base 1 and base 2 are always parallel to each other. That's how you can tell base 1 and base 2. And then the height is the one we haven't touched, 4. So 1/2 times 6 times 4, 12. Okay. Okay, so what's the answer to B? What's the answer to B? -12, yeah. The answer to A should have been -12 too, but I didn't put -12. It should be -12, yeah. It's asking the same question. It's asking the same question. The only difference is between those, one is just saying it, one is actually notation. The notations are different, right? So this is going to be -12, yeah. That was the same thing. Okay.
So when they're under the x-axis, they're always going to be negative.
Always negative.
So even if, like, for some reason the numbers were like negative,
Mhm.
or whatever,
Yeah.
in the end the answer would always be negative.
So yeah, if your area is underneath the x-axis, always negative. Always negative, yeah. Any area underneath the x-axis is always going to be negative, yeah. Because I got +12 when I did the math, but because it was under, it had to be -12. That's why I put -12 there. Okay, last thing. We'll probably finish today, and then tomorrow I'll just give you guys time to do the practice, because this is going faster than I thought. Okay, so last one. Okay, so they give us a little bit of info. They said given, hey, the area of sine from 0 to pi is positive 2. Use that to answer the rest. Okay, so first thing I'm going to do is I'm going to draw a picture. I'm going to draw a picture of the sine, one cycle of the sine curve. What do I mean by one cycle? From 0 to 2 pi. So one cycle means once around. So from 0 to 2 pi. Okay. So I know that it starts at 0. Sine of 0 is 0. And then sine of pi over 2 is positive 1. I'm just going right off your sheet. And then I know that pi, sine of pi, is 0. And then I know that sine of 3 pi over 2 is negative 1. And then 2 pi is the same as 0. And then it's the sine curve's got this guy, it looks like this. Okay. And then it continues, it oscillates. It goes back and forth. Keeps going back and forth. Every 2 pi, goes through one cycle. Okay. Okay, so that's what I know. Now it tells me the area from 0 to pi is positive 2. I'm going to highlight this same color because that's what this is here. Said it's positive 2. That's what it tells. That's the given part. I'm going to use that to answer the rest. Okay, so A, now they want me to go from pi to 2 pi. That's down here, right? Take a wild guess. What do you think that's going to be? Negative 2, yeah. How do we know it's negative 2? Because it's symmetrical. Yeah, it's symmetrical. They have the same exact values over here, they're just negative. The same values over here as over here, they're just negative. All right? So the same values, just opposite, means I'm going to have the opposite number here. So this is negative 2. Good. Okay, what's B then? Yeah, because aren't you just adding them together? You're just going from 0 to 2 pi. You're just going, what's the area under the curve from 0 to 2 pi? Well, you're going to add that with that, and you're going to get 0. What about C?
Positive 1.
Positive 1, right? Because isn't it half of the green? It's just half of the green, right? And we know, again, we know it's symmetrical because we have all the values. So that would be positive 1. Good. What about D?
0 again.
0 again. How do we know it's going to be 0 again? You're absolutely right. D is going to be 0. How do we know that?
It says from 0 to negative pi is symmetrical. And it's
Yeah, so negative pi would be over here. Same distance as this guy here. So it'd probably be over here somewhere, negative pi, right? And it's oscillating, so it would look like that. So that would be negative 2. So it'd be negative 2 plus 2, you get 0 again. Let's see, let me move this a little. I'm just going to move it over here. Last one. Last one and we'll be done. And then if you guys have questions on the practice from yesterday, I'll be happy to answer. Okay, so here we go. E, 0 to pi. Okay, so I know it's 0 to pi, so I know it's the green. So is the answer going to be 2? No. Because it's got that 2 here, right? What does that guy do to that guy?
It moves the starting point up to.
There you go. It moves every dot up 2 units. Up 2 units. So this is what it's going to look like. Very similar, but just a little different. So we want to go from 0 to pi, right? So we're going to go pi over 2. I'm not going to draw the whole thing because it just wants from 0 to pi. Has the same shape, just up. So 0 is not at 0. It's at 2. Pi over 2 is not at 1. Where is it at?
At 3.
It moved up 2, so it's going to be at 3. Pi is not at 0.
Is that 2?
It's at 2, right? Still has the same curve. Still has the same curve, right? That same green curve is here. And we know but I have to shade to the x-axis, right? So what it does is it creates more area. It creates more area. And don't I know that little cap, that little dome on there? What's the area of that little dome?
2.
So I already know the area of here is going to be 2, right? So all it did was create a box. What's the area of that box? 2 pi. It's pi width, 2 height, 2 pi. Add them together. Which you can't because one is a pi and one doesn't, so it's just 2 plus 2 pi. Because that guy is just a vertical, it's what we call a vertical translation or a vertical shift. It just created a vertical shift up 2 units. It was a vertical shift up 2. That's all it did. Okay? All right, so we got about 10 minutes. So questions, were there any questions off the top? I can answer some tomorrow too, but